Today we are going to talk about conic sections. Just as the name sounds, it's just curves or surfaces that can be formed by on a cone, but not just anyhow. Imagine you take a plane and you cut across a cone, in this case a double napped cone. So let's say here you have a cone, here you have one cone, and you have another cone of the same type along the axis, joint at the vertex. If you take a plane and you cut across this cone with this plane, then you are going to have various surfaces, various curves defined by the intersection of both. And those curves that you can have from this intersection is what is known as, so let's say this is the intersection, not perfect. So the curves defined by the intersection of this plane and this cone, in this case, I just cut through the upper, I just cut across the upper cone, but you could be cutting both cones, like this, for example. Okay. So the curves that are defined in each case by the intersection of this plane and the cone is what is known as a conic section. And in order to be able to characterize this surface, we need to introduce a number, a very important quantity known as the eccentricity. E. And the way this is defined is the ratio, so it's defined as P F on P D. So the eccentricity of a conic section is defined as the ratio of the distance of any point on the surface of the conic. It could be maybe this surface. Let's say you have the point P on the surface of on that curve, on the curve defined by the given conic section. So the ratio of the distance of the point P to a fixed point, F, known as the focus, to that of the distance from P to a fixed line, known as D, which we call the directrix, should be a constant. So the ratio of the distance of a point P on the surface of the conic section from a fixed point to that of a fixed line should be a constant. That constant is known as the eccentricity. Based on this, there are four types of conic sections that we can have. If E lies between 0 and 1, then we get the first conic section known as the ellipse. If E is equal to 1, we get the second conic section known as the parabola. If E is greater than 1, we get the third conic section known as the hyperbola. And if E is equals to 0, I ought to have put it first, we get the fourth conic section known as the circle. So, knowing the eccentricity of a conic section, we can infer which type of conic it is, whether it's a circle, an ellipse, a parabola, or a hyperbola. So let's start with the first conic section, which is the circle. So the Cartesian equation of a circle is defined as, is given as x minus h squared plus y minus k squared equals to r squared. So what this equation means is that a circle is the locus of a set of points. Let me draw. So we have a circle that is defined by a center of coordinates h and k in the plane. So what this equation means is that a circle is the locus of a set of points, P in this case, of coordinates xy, defined such that the distance from a fixed point of coordinates hk, which is the center, is a constant. That constant is known as the radius. C here is the center, and P are the set of points. So as P moves along this curve, which in this case is a circle, the ratio, the distance of P to C is always a constant. That constant is known as the radius. So it is expressed by this equation, where h and k simply represent the center of the circle, the coordinates of the center of the circle. So it's really, really easy to understand. The second conic here, which is the ellipse, so an ellipse which has an eccentricity between 0 and 1 is defined as the locus of a set of points which move in such a way that the sum of the distances from the two foci, as we're going to see, is a constant. So it has as Cartesian equation this all over a squared plus y minus k squared all over b squared equals to 1. So if we want to represent that, x, y. So let's say the center, in this case, we put the center at 0, 0. So h and k are both 0. We have this. A is the distance from the center to one of the vertices. So these are known as the vertices. So this is A, and it's known as the semi-major axis. So A here is semi-major axis. And B is the semi-minor axis, which is the distance from the center to the second axis of the ellipse. So this is B. And then the foci are here. There are two of them. The first focus is here. We can call that F1, and the second focus is here. We can call that F2. So what this equation means is that an ellipse is a curve defined in such a way that we have the locus of a set of points P, of coordinates xy, which move in such a way that the sum of the distances from the two foci is a constant. So if the distance from the first foci is d1, and from the first focus is d1, and the distance from the second focus is d2, d1 plus d2 should be a constant. And this is how an ellipse is defined. Okay, let's move to the third conic section. Let's change paper, which is the parabola. Which has eccentricity equal to 1. So the eccentricity here already defines the nature of such a curve. It would simply be the ratio. It would simply be a set of points which move in the plane in such a way that the ratio of the distance from a fixed point, known as a focus, to a fixed line, known as a directrix, is 1. As easy as that. So the general, the Cartesian equation is given by y minus k. So we assume we have a center hk equals to 4p times x minus h. So p here represents a parameter, which is the distance from the vertex to the focus. I'm going to illustrate that. So let's say we have, okay. So let's say we have a parabola like this, okay, that has its vertex at 0, 0. So h and k here represent the coordinates of the vertex, h, k. So the parameter p here is the distance from the vertex to the focus. Here there is just one focus, so this is p. But it's also the distance from the vertex to an imaginary line that we called the directrix before. So this distance is also p, and that line is the directrix. As such, if you have any points on the surface of the parabola, then the ratio of the distance from this line, so this distance to this, is 1 in this case. Okay. In other words, the point P, wherever it's going to be on this curve, it's always going to be at the same distance from the focus, F, and the directrix, Z. So you can kind of picture that out. And the last conic section here is the hyperbola. Which has an eccentricity greater than 1. So a hyperbola is defined as a set of points. So imagine this time around that you're having a set of points that move in the plane in such a way that the difference of the distance from the directrix, the difference of the distance from the two foci is a constant. So represent that with this Cartesian equation, x minus h squared on a squared. So in this case, we have a minus. If you remember, for the ellipse, you have a plus. So you're just going to put a minus here. So that's y minus k and b squared equals 1. So if you want to represent that, so let's place the center of our hyperbola. So hk again represents the center, the coordinates of the center. Let's say we are at 0, 0. Okay. We're going to have two portions of the curve that defines the hyperbola, like that. Here you have the x-axis and the y-axis. So in this case, just as with the ellipse, if you recall, we had two foci. So here we also have the two foci, but they are not contained inside the area defined by this. Like here they were inside the area defined by the ellipse. In this case, they would be here. So we're going to have F1, and here we're going to have, so in this case, you're going to have F1 here, not here, and you're going to have F2 right here. And again, you can imagine that we have two imaginary lines. In this case, the directrices, D1 and D2 here. So imagine them having a point, our set of points P here. They move on this curve. And always the ratio of the distance from this focus, so this distance, so the difference of this distance, the distance of P from the first focus, D1, and the distance of P from the second focus, D2, is a constant. So D1 minus D2 is a constant. The set of points has as Cartesian equation this, and is known as a hyperbola. So A, in this case, as you can imagine, is the distance just as to the ellipse. If you remember, A was the distance from the center to the vertex. It's the same here. A is the distance of the distance between the vertex and the center of the hyperbola. This is A, and it's the same distance the other way. And then B is a parameter that would kind of determine the shape of the hyperbola. And what's really particular about the hyperbola is that we can define two other lines known as asymptotes that are actually tangent to the hyperbola at infinity. In other words, imagine having two lines like these. Okay, let me put that in red. Maybe it's going to be more visible. So like that. And like that. So these two lines, you can see, they would never touch the these two lines would never touch the hyperbola. They're going to get very, very, very closer to each other, but they will never touch. And these lines in mathematics are known as asymptotes. They are tangent to the surface, to the curve at infinity. So it's also possible to express these equations in polar coordinates. So let's look at that. So if we're in polar coordinates, where any point is defined by a distance, small r, and an angle theta, we can apply the transformations x equals to r cos theta, y equals to r sine theta, to transform the equations that we saw into polar equations. And we can show that, in general, the conic sections have as polar equation r equals EP divided by 1 plus minus E sine of theta. Or you can also have cosine of theta. It just depends on how the axis of your conic section is oriented. You can have the main axis parallel to the y-axis, or the main axis parallel to the x-axis. So in any case, you need to determine the eccentricity in order to know which exact conic section you're dealing with, as we defined earlier. Okay, so that's the little summary on as far as the conic sections are concerned. Hope you find this interesting. If so, please drop a like, then subscribe, and see you soon to talk about another interesting topic. Until then, remember that physics, and in general science, is believing that we can describe nature simply and consistently. Is that not nice? I know you find that nice.